How many of you guys are going to the play tonight? No? Tomorrow? Okay, 1 or 2. Saturday matinee or night?
I have no time.
Oh. Maybe for English, I don't know. Ask your English teacher. For me, I'm just saying it's good to support your fellow classmates. Or Team Nicaragua American Indian. I'm trying. I think Mr. Auger might be going. I think Mr. Shea might be going. I think Katrina, maybe some family. I don't know. Some alumni that are randomly going. Kiddos, is there anything really super new on this page? I don't think so. Maybe some of the names are a little new. P.S. Sorry, really quickly. Jonathan and Colby, there is a part 2 to the test. Remember calculator, non-calculator? So I gave you the non-calculator part, which is fine. Both your calculators are off to the side. But when you're ready, the calculator parts are waiting on my desk. Just bring those over, put them in, take out the others, and then you can use your calculator. Okay? All right. Shouldn't be too much new. We know that the vertex of an angle is the point where they come together, the two line segments, or I should say the two rays come together if we're going back to geometry. The vertex will always be at the origin for an angle in standard position. The normal rotation or the positive rotation is always counterclockwise, which is up and to the left. That's how you positively measure an angle. A negative angle is going to measure clockwise or down and to the right. Let's see, what's something we haven't measured, or not measured, labeled? We might want a quick little reminder of the quadrants, quadrant 1, 2, 3, and 4. We'll definitely review him quite a bit, or those quite a bit, I should say. I assume that you know what those quadrants are, but just in case, a quick little reminder. And last but not least, initial and terminal sides. You guys know the words initial and terminal, right? Initial is like at the start, at the start or at the beginning. So it's the beginning side, so any normal standard position angle starts at the positive right axis. When we're just talking about an angle in math, you can think about it starting. Initial side is the positive x-axis, and then it comes up and it ends, terminal, ending. It ends on the terminal side. Frequently named with Greek letters. Let's review your Greek, huh? Alpha, beta, gamma, delta, epsilon, zeta, eta, theta. Iota, kappa, lambda, mu. Okay, you only need the ones that are ready, set, go.
On the previous page, there was like, is there a circle with a slot? Was that supposed to be for a representation?
That's a theta.
Okay. I was unsure what it was. This is Greek.
It's just a representation. It's all Greek to you. On the left-hand side are the capital letters, on the right-hand side are the lowercase letters. For alpha, for instance, even though it looks all cool and snazzy, just think of it as like a little interlocking circle, or an ichthus that's backwards. Do you guys ever do the fishing when you were little? The little fish in the sea? Like that, but without the tail. And backwards. Beta, gamma. Gamma just has a little tail to it. Delta's like a D. The theta has a little curly Q on top. Epsilon kind of boring. Theta is a really important one. And some of these you guys have seen in other classes. At least some, like gamma rays. Delta, the triangle, the capital delta, you guys have seen in math, meaning change in delta y over delta x. Mu shows up in physics quite a bit, lambda does as well. Pi, of course, you've seen. So you should know that one. In the Bible, if you read the Bible at all, alpha and omega, beginning and the end, thinking of the alphabet.
Do we only do the highlighted ones?
Yeah, you can do the highlighted. Unless you want to go above and beyond, that's kind of fun, but just the highlighted ones. Sigma, you don't really need to worry about the second part to it, of the lowercase. The first part's probably okay. What we're used to seeing more is the capital sigma. It actually has to do with sequences in series. with summations. I think you still see that in Algebra 2. You definitely see that second semester of pre-calc. Well, definitely honors pre-calc. They should see it in regular also. You guys have seen some of these in like movies with sororities and stuff like that. Like omega, beta, theta, alpha.
For pi, the capital one, it's just one line, right?
Yeah, just one line. Just like a tall. You guys didn't know you were learning Greek today, huh? Just the alphabet. Depending at some classical academies these days, they do have, well, it's usually more Latin than Greek, but the classical academies have Latin classes these days. But Greek wouldn't be too bad, especially for Christian schools. Okay, so we're not going to use all of them, not necessarily, but if we do need to talk about multiple angles instead of calling them angle 1, 2, 3, and 4, which is kind of, I don't know, geometry-ish, we might name them Greek letters instead. So if we already have a theta, for instance, you might go with an alpha or a beta. Usually we won't use, I'll put some of these in parentheses as far as angles. We won't probably use delta because that's already given another mathematical meaning with our change in. Won't use pi because obviously we use him as 3.1415926. Won't use sigma, not usually because we use him as a summation. If you were in other classes, I might take out the mu, take out the lambda, but right now, epsilon. I might take out epsilon just because we do have normal little e standing for our natural number, 2.71828. So even though epsilon is used in math a lot, maybe I won't use them. But they're good for just normal STEM classes in general to know some of these letters. I think we're close. I know some of you guys are agonizing a little bit more over the letters than others. But once again, we can name angles not just with like geometry, 3 points, which we're not going to be doing 3 points since we're not really doing triangles much. We can also name angles ourselves with Greek letters, and especially we're going to be using theta a lot. Just the lowercase one. It's not going to be a 0, just be careful. You don't want to think about it as being a 0 or an empty set. That means none. That means literally there are no answers in the set of answers. So make sure that your line goes straight as much as is possible. Or if it's straight up and down, you can make it one of the other letters, but not diagonal, not diagonal, or else we're in trouble. Okay, radians. Radians. Let me give you a second. You don't really need to skip any lines, I don't think, but I think the pictures will be useful. What is a radian versus what is a degree? That's a question we're going to try and answer today. What is a radian versus what is a degree? What is a radian versus what is a degree? Yeah, that's okay. That's the label for that. finish writing. Okay, one person from every group who's done writing, grab the string. Caroline, I'm gonna have you come move up in this seat right here. Toby, you're gonna join their group, and then Abby, you're gonna join Jackie, Andrew, and Caroline. So then you guys already have one. I want you guys in your groups really quickly to start scoping around the room for some sort of circular object that is bigger than, maybe not bigger than. Bigger than a pencil or pen, let's put it that way. Some sort of circular, it can be cylindrical, it just needs to have some sort of circular component to it. Some circular object in the room that is bigger than your pen. It needs to have some sort of actual length or distance to it. Yeah, Karen, you can move up close. You can take your notes, just for a little bit. Scope out, some sort of circular object. I have like cans of things. I have like a gear Rubik's Cube circular puzzle in the back. I have cups. You guys have vases. There are water bottles. Ready to go, get a circular object. Or there's some sort of... Oh, someone's water. I think she's okay. Some sort of circular object has some sort of circular component to it. Kind of circular base. I have a Clorox wipe, Lysol wipe container up there. That will work. I have... Don't take that cloth off the wall. That could be scary. I have a roll of tape. I have like a Lysol can of disinfectant. I have a roll of paper towels. I have a cup. I have my gear Rubik's Cube thing back here. I have another coffee cup. Okay, does every group have at least something that's circular?
Yeah.
Now, here's what I want you guys to do. First of all, with that circular object, you guys can go to your workspace if you want to write these things down. I have a ruler up here on the podium because your string is just going to be your measuring tool. Does anybody have a mom that sews?
Yes.
Is that not a thing anymore? A mom that sews, they usually have a flexible measuring tape. Right? Or if you've ever gotten your measurements done, like you get in a wedding or for like prom or something or others, there's a flexible measuring tape they use. Why? Because you're trying to measure something that has some sort of curve to it, right? That's what you're doing with the circles. Now here's what I want you guys to try to figure out. All of radians are based on R. And what does R stand for? So what I want you guys to do in your group really quickly with whatever object you have is try to approximate the radius of your shape. Wherever the circle is in your shape, try to approximate the radius. So use the string, maybe you can go all the way across. What would that be? Diameter, and you want to go all the way across in a way that goes from one end to like the exact opposite end. You can do the diameter, measure the diameter, and then cut it in half. Or you can take the diameter and then you can fold it in half and measure the radius. But either way, work as a group, try to approximate your radius. You can come up here to the ruler once you think you have a measurement. You can use the ruler. My hint would be maybe the diameter.
Say this is about.
Or we could use this.
Yeah, some others are harder than others to figure out.
Okay, let's find the radius. It's a little more. It's like 6.3. Is it 7 or 11?
You can do either one, whatever is more precise, but you have to bring your string up. The ruler has to stay here. So you can bring your string up. There you go. That's probably the easiest one. Whatever you think is more precise for whatever approximation. Just make sure you write down which one it is, centimeters or inches.
They go all the way across. It's probably going to end up about 2 inches.
That's what I was thinking.
Which is going to end up being about 12.
You always approximate one significant figure.
That's what I was thinking.
Nice. Look at that training.
I wrote my longest.
So proud.
Well, this is actually nice.
I got 4 minutes.
Well, it'll give you about.
Okay. Now, once you think you have an approximate for your radius, I would write it down if I were you. If you're trying to have like to the nearest tenth, that's not a bad idea. want you to figure out how many of those, well, let's say it this way. I want you to make the radius, whatever shape you have, you guys should all have different radii, right? Probably most of your shapes are different. Okay, whatever radius you have, I want you to pretend that that's 1 unit. So 1 unit for you is whatever your radius length is. I want you to figure out how many radii, how many of those would it take to go all the way around your circle? How many of your radii would it take to go all the way around your circle? There are many different ways of thinking about this. But how many of your radii would it take to go all the way around your circle? One way of doing this is to take the circumference, measure all the way around your circle, and then divide it by the number you think is the radius. So why don't you try measuring around the circle? Take the string, measure it around, approximate what the circumference is, and then try dividing it by the radii. Let's see how many radii are in your circumference.
Probably did something.
Figure out how many radii are in your circumference.
How many really?
Have you guys
I forgot, I didn't send out.
She starts off with
Yeah, Carly might need to help her hold that up. It's kind of hard to.
Hold on a second. I'm sorry.
Did you get the diary?
125. Let's measure.
I'm sorry.
Maybe try measuring all the way around. Approximate that as best you can.
So basic circumference.
Just go like walk up to them in front of you.
Okay, okay.
Circumference of pi r squared.
2 pi.
2 pi r.
But technically, you're trying to figure this out without knowing the constant pi. Oh, right. So is your string visible?
We'll figure it out.
I got ass.
And if I find
Oh, you
half
can
of it, I
add
can just
in here,
multiply
like,
it by
whole
2.
It's just
Try to hold it
interpreting
around to get as precise as
finding
possible.
what the is.
Does anybody have a really long string?
Okay.
I forgot what you
So
get.
Okay, the radius is 4.41.
4.41.
Yes.
That's okay. And you just multiply this by 2.
Divided by
I didn't know there was an object big enough to add one.
And then I put my thumb, and I half
Okay.
it.
That's 470.
Yeah.
I got 5.1.
Answer the question we're asking, you're
So
answering.
we're trying to figure out how many radians
How
it takes to go around the circle.
radii
Another 6.5 plus 6,
Two.
18.5 times 2,
Go.
37.
Here we have the dime.
all
It's gonna take
around.
14. It's gonna take 14.
So this circumference is 3.7.
So,
You divide by
just
6.25.
the circumference by 5.92.
Basically, how many radii would it take to go all the way around a circle? Your circumference divided by r.
Oh. 14 divided by 2.
Yeah.
So it's like 3.6.
Yeah, that's
14 divided by.
You're at 6 or?
Well, 6.
You divide by 6.5.
6 radians. About 10.
I'm gonna ask you guys for this in just a second. So you're taking your approximate of the circumference, dividing it by the radii to ask or to answer. How many radii would it take to go all around the circle that you
So, yeah.
How many radii would it take to go all around the circle?
That's about it. We got pretty close. We're only 2 off. Well, we did the way you said, and then I double checked.
I get to be 3 decimal places.
Oh.
3.1.
All right, we have a few groups that are still working on it, but let's go and get some of these numbers down. So how many radii would it take to go all around the circle? Group number 1, what'd you get?
6.
6?
We rounded up.
So it's 5 point something and rounded up to 6? 5.5-ish? We'll try to be precise, 5.5-ish.
Okay. Was it 5?
No, now they're gonna go.
5.5. Okay, you guys, what'd you get? It's
Oh, wait,
group
no.
2 and 3 technically.
No, that exact number.
No?
5.92.
5.92? You guys still working on it? Oh, you have it, Dean? What do you got?
That's 6 times.
Like 6, 6.
Roughly.
Huh?
Around there.
Was it a little bit above?
I don't know.
Okay, we'll just say 6 even. A little bit above would have been good though. You guys, what'd you get?
3.18.
3.18? Okay, that's an outlier. How about you guys? 8. Ooh, even more of an outlier. Okay, first of all, is there some error? Yes, there is some error. What should it have been precisely? What's the circumference formula? Careful. 2 pi r. Diameter times, which is 2r. Diameter times pi. Another way of saying it is, how many, you guys did c over r, right? How far around over how far across divided by 2. Do you guys divide the across by 2? Ah, haha, actually, theirs might be the best approximation. If they didn't divide by 2 with the across, you guys did the diameter, so you could have actually been, oh, really staying close. If you divide c by r, what would you have left? My bad, 2 pi. If you divide c by r, you should have 2 pi. If you divide c by d by the diameter, you would have had pi. So what would 2 pi be? What should you guys have gotten if you had done the measurements precisely and had probably a little bit better instruments and circular objects? What's the answer to how many radii to go around the circle? Okay. That was the right answer. Did we get close, some of us? Yeah, not too bad. Some of you guys are like, I think it's 6-ish. I think it's 6-ish. You're right. Just the decimals were a little bit off. This one, if you guys forgot to cut it in half, then yeah, yours is super close. And then this one, having a little too much fun. But, coming back. What on earth does that have to do with radians? Kiddos, count how many, if you were to take a radius, and if you were to split your string with little tick marks at every radius, making them the units on your ruler. So not inches, not centimeters, but if you were to make your own ruler, a flexible measuring tape, and if you were to mark 1 radius, 2 radii, 3 radii, 4 radii, how many would it take? 1, 2, 3, 4, 5, 6.28. A radian is really just a radius as a flexible ruler measuring around a circle. So if I was to ask you for where would 1 radian occur, you would take 1 radius and you would say, okay, what if I was to mark a ruler? A flexible measuring tape, if you want to think about it that way. If I was to take a ruler that could bend around the circle, I would take 1 radius, I would tick mark it, and I would fold it, and guess where that 1 radian would hit? Right there, in the first quadrant, approximately 60 degrees. Where would 2 radians hit? You would fold it around the circle, and as you fold, it would hit right here at 2 radians. Where would 3 radians hit? Right here. And why does that make sense? What do you guys know about 180 degrees? It's 3.141596 radians, which means that's how many radii, if you were to make a little ruler of how far from the center to the outside, that's how many radii would naturally curve around to form a half circle. What do you know about how many radians are in 360 degrees? Exactly. Because that's how many radii it would take, that's how many tick marks of radiuses on a flexible ruler it would take to measure all the way around. Now, you guys had string, you guys had a ruler, and you guys had some pretty irregular circular shapes that hopefully I get back before you leave. But you still were able to get most of you around 6 as far as being the ratio. So how on earth do people get more precise? Well, with math, with better instruments, and eventually with technology. And now people are calculating who knows why or where, but billions and billions of veggies of pi. We have supercomputers at this moment working to try to find some sort of pattern to pi. Possibly it's because they want to figure out some sort of explanation as to why this random number shows up in so much of nature. They haven't been able to find a pattern. Still irrational. So, who is pi or what is pi? who is pi or what is pi? Technically, if we were to take our little c equals 2 pi r, which does have to do with, literally, can you measure around and across a circle? Yes. You guys did with string, maybe not super precisely, but you were able to approximate it. You could say that pi is equal to, and this is only because we figured this out after the fact, we could say it's c over 2r or c over the diameter. Which is why the group in the back, they got 3.18, and I was like, whoa, that's like pi. Because they divided, I think, by the diameter, not by the radius. And they got a pretty good approximation for pi. The rest of you guys would have had around like 2.7, 2.9, which is still 3-ish, but a little bit off. So what is pi? He is the relationship of the distance around a circle, or the ratio of distance around a circle to the distance across a circle. Now, there was one little random formula back here that we didn't talk about. The S one, what's going on with him? Let's label just a couple things. S is actually the arc length. And remember, arc length is just the measure. If I was to cut an arc and straighten it, it's how long that arc would be. It's just the length of an arc on the outer edge. Radians measure the outer edge of the circle. So it's arc length over radius. It's arc length over radius. And that's how we can find our theta. So it's basically taking the measure around, but sometimes you don't go all the way around. So that's another formula that might show up. We might use it from time to time. That's not really the purpose of this section. The purpose is to give you a better understanding of what a radian is. It's not just another way of measuring, but it actually comes naturally from any circular object that you could possibly find. So the most common radian measures. Ironically, not 1, 2, 3, 4, 5, 6, and 6.28. Because those ones don't fit precise angle measures. Instead, pi and 2 pi are the precise angle measures, or 180 and 360. So then we start cutting pi into smaller fractions, and we start getting our special angles from them. So, unit circle's coming. But to get to the unit circle, I want to make sure that you guys understand radians. Because if I was to ask you right now, where does 7 pi over 6 show up? What quadrant? What would you guys answer?
Third.
Good. This time don't just go on your fingers, because I only had one person actually said something. How about 5 pi over 3? What quadrant?
Fourth.
Don't say anything. Just show me on your fingers, but good.
Whatever.
How about 3 pi over 4? Show me your fingers. Your best guess. 3 pi over 4. Your best guess in 5, 4, 3, 2, 1. Okay, a lot of you guys got the 2, but just a few of you guys are still kind of wobbling between 3 and 4 and 1.
Cool.
Okay. We need to get a good understanding of, first of all, who is pi, what angle measure is pi, and who is 2 pi. If we can get a good understanding of that, you guys can have a good understanding of where all the other special unit circle angles occur in radians. Now, hold on, let's quickly go to the degrees really fast. Does anybody know what pi over 6 is in degrees? We have a conversion that we'll talk about, all that jazz. Does anybody know what degree this is? Pi is 180. Does that make sense? And we're cutting him in 6ths, so that'd be a 30-degree angle. What would pi over 4 be?
45.
Cut 180 in 4, it would be a 45. Or you can think cut a 90 in half. What would pi over 3 be, or 180 cut in thirds? 60. What would be a pi over 2? 90. This one, 180. This one, 360. So you go all the way around. If I was to ask you what a degree is, that would be much more complicated than a radian. It's a contrived little tiny baby arc that is 1/360th of a circle. Like, how do you measure? I don't know. But our brains, for some reason, probably because of some applied mathematicians back in the day, probably literally people who would do navigation on the sea, probably like oceanography. Because radians would be much harder to practically use, as opposed to having like a protractor with a degree. a lot of different angle stuff came from charting ocean travel. But anyway, coming back. So you have 30s, 45s, 60s, 90s, 180s, and 360s. All of it comes down to the pi being halfway around the circle, basically 2 pi being all the way around. And you can use these fractions to help you out as far as what types of reference angles you're working with. Now we're going to come back to that, but let's go ahead and keep on going. Talking about coterminal angles. Because the point of this section is actually not the unit circle, it's more of an intro. Unit circle is next section. We're just trying to get the basics down to all sorts of different, well, the basics down about angles, let's put it that way. Co-terminal. Co, with or together, something is in common. Terminal, guess what's in common? The terminal side. AKA, they end at the same place. Angles that end at the same place or share a common terminal side. So question, what if I was to give you some sort of angle like, oh, I don't know, say that equals, let's do 3 pi over 4, because we're trying to work with radians. Slowly getting you guys back into what radians are. 3 pi over 4. A lot of you guys figured out this in the second quadrant. Can anybody figure out what the degree measure would be in the second quadrant if it's an over 4? What kinds of angles do we say were over 4?
135.
Yeah, because we can take 180 and say, okay, well, we're cutting 180 into fourths. So if we're cutting it into fourths, 4 and 18 is 4, 32. They're 45s, but how many 35s do you have?
3.
You think of, okay, whenever I have a fourth, it's 45s, and I have 3 of them. Okay, so then, there's 1 45, there's 2 45, and there's 3 45. I take pi and I cut it in 4 pieces, and I go 3 of them as I rotate. 1, 2, 3. Or you can think I go 3 45s, so 3 half 90s, so there's 1, 2, and 1 more. But either way, you do get to 135. Can anyone tell me any other way of getting to this exact place of 135 degrees or pi over 4 without going or going a different way than 3 pi over 4 or 135? Okay, so one way is that because we want a positive and a negative coterminal. So we could also say we'll get to the exact same place if we go negatively, which would be, if you count it, 1/4, 2/4, 3/4, 4/4, 5/4. Anybody figure out what that would be in degrees? 5 pi over 4 in degrees? How many 45s is that? That'd be 5 45s, right? Yeah, so it'd be negative 225. I need the negative or else it's not going to work. I need to go the opposite direction. So I go negative 5 of those fourths, or I go negative 5 of those 45s. That's how to go negatively to the same place. That would be a coterminal angle. It ends in the same place. But what would be another coterminal angle? It's not even beta. That goes positive instead.
7.
Not 7.
11 pi over
7 over 4 is a little less than 2 pi, so he's not even going to make it all the way around. I need him to get over here.
4.
Why 11?
Because it goes around, and then it goes 3 fourths more.
If you go 5 pi over 4, you need to go another full 2 pi to get back around. How many fourths is in 2 pi?
8.
How many fourths is in 2 whole? 8 pi over 4 plus 5 pi over 4 with
No, it's 3.
it's 3 pi over 4. 8 pi over 4 plus 3 pi over 4. Or another way of looking at that would be in degrees. 360 plus 135, which would be 495. Has anybody figured out the blank that you need to fill in? How far away are these coterminals from each other? What's 135 minus negative 225? 360. What's 495 minus 135? 360. Or what's 3 pi over 4 minus negative 5 pi over 4? 2 pi. Or what's 11 pi over 4 minus 3 pi over 4? 2 pi. Coterminal angles are always going to be one full revolution, or we could say one full rotation away from each other, because to get back to that same placement in revolving, you have to go all the way around. You guys have felt this before, I think. Let's see, what's the way we can do it? Has anybody ever done one of those old alarm clocks? Where you have to change the hour and the minutes just by hitting like up or down? What happens when you pass where you want to go? Because it only goes one direction. So if you're thinking, if you pass the angle, how do you get back to it? You have to go a full revolution again. So you're going to have to go a full 2 pi or a full 360. So we could say two angles, I guess I said use phi instead, of, is it phi or is it phi? Phi, pi, 4 phi. I smell the blood of English. We just have to say that a coterminal angle is going to be the initial angle plus 360n. I'm making a little formula. Or, oh, it looks good. I think I italicized it. It's supposed to be italics, but then it looks funny because then it's slanted. I could say 2 pi n, but here's the kicker. For both of these, n has to be an integer within the set of integers. Another way of saying that is n has to equal positive or negative 0, 1, 2, 3. Why couldn't n be a rational number? Why couldn't it be a fraction or a decimal? What would happen if I had a fraction or a decimal times 360 or 2 pi? Would it get all the way around? So I have to have full multiples of quantities. Does that make sense? I have to have full multiples of 360 or 2 pi. Okay, so those are coterminal angles. To get back around, you have to add 360 or 2 pi. You have to go one full revolution. Oh, this is from geometry. What's it mean if two angles are complementary? Well, that's the same thing. That's congruent. Careful. Yeah. They sum, well, technically two acute angles. They have to be two acute angles that sum to be 90 degrees. Ooh, and what was 90 degrees in radians? 1/2 of 180, which is 1/2 of pi. Okay. Supplementary, they add to be, or sum to be 180, or pi. Complementary, you have to have the sum of two angles less than 90 degrees. In supplementary, you also have to have two angles whose measures independently are both less than 180. Meaning you can't have like a bigger angle than 180 and a smaller angle add to be supplementary or add to be complementary. So if I was to give you something in radians like pi over 6, which is the same as what angle measure?
30.
What would be his complement and what would be his supplement?
So I was 150.
Okay, those of you that can do degrees really fast, you can get it in degrees pretty quickly. And that's not bad. We just need to expand that to also make you that quick in radians. So, supplement would be 150. I heard Andrew say it. What would the complement be? 90 minus 30 is 60. Cool. But my question to you is, what would that be in radians?
Pi over 3.
Careful. I have 1/6. I have 2/6 left. Oh wait, 2/6 is what? Pi over 3. So So I would need 2/6 to get all the way to halfway. I have one. I would need 2 more, but 2 over 6 is pi over 3. And how many sixths would I need to get all the way around? 1, 2, 3, 4, 5. The more you visualize the unit circle, for any of you that are at all visual in your comprehension of that, the more you can think about it in fractional pieces, the easier it will be. But are there conversion formulas to get from degrees to radians or vice versa? Yes. And so that's probably the one thing we're not going to really get to today. Especially if our notes freeze. What I'm going to do is if you wanted to go from the degree to the radian, to multiply by 180 over pi. And if you want to get from a radian to a degree, multiply by 180. So I said that backwards. All right, we'll take, you guys account 4.1. If you took any of my circular objects, just put them in a safe place and we'll have some safe with them. Pi numbers. Think about it as a piece of pie. We'll talk about it tomorrow. We're going to think about pies as how those. Homework fellows in the front, thank you guys. Sorry, not behind you.
I couldn't stand it.